Hello, my name is Vihan Akshay, and this presentation summarizes my work as part of my DDP for the last semester. The title is Cascaded Deep Monocular 3D Post Estimation with Evolutionary and Synthetic Training Data, and this is part of a longer project which is called Unsupervised Behavior Recognition using Deep Reinforcement Learning. So, to talk about the motivation of the project, uh, animals with time have developed a complex behavioral repertoire, and we wish to understand that better. And for us as human beings, physical movements of these animals are the easiest to observe. And we know that these pattern of movements are because of inherent gene metabolism, neural signaling, and all that. So we're trying to build unsupervised algorithms which will aid us in understanding the underlying biological mechanisms that drive the animal to make the decision it makes, and also the principle behind generation of these behavioral sequences. Okay, so this is the pipeline of the overall project. So what it basically does is it takes in the input of a video data, and with the help of pose estimation module, it determines poses. So that's basically you give a video input and then it'll tell you key points. And these key points are used to generate trajectories. So we frame it as a reinforcement learning problem where we say, okay, so this is the pose it's in right now, S0, and it has moved its arm. So that's action one. And it goes to S1, and we make trajectories like that, and we try to identify behaviors based off of these trajectories. So the pipeline is like this: so video data, we get posts, we get those key points, and from that key points we do some pre-processing to obtain trajectories, and from trajectories we use this RL framework to obtain options which are nothing but behaviors. With this already existing, our goal for this term was to improve the state representation, because we felt so right now the project uses 2D key points for state representation, and improving the state representation should yield better discovery. And so the ultimate goal for this term was to improve the post estimation model. So right now the post estimation model used is basically what we discussed in the previous slide. There's video input and it gives you 12 key points as we can see in the mouse. Sorry about that. So it just outputs these 12 key points, which are 2D coordinates. So you basically get 12 cross 2 for each frame. Not exactly frame, but for each state representation. And we want to improve that. So to do this, one obvious and viable choice for better state representation is 3 dimensions for each point, and not just 2. This is because uh, like intuitively we can say that the mouse makes the decision of moving some arm or some leg or something, and this majorly is decided or is affected by the body structure, right? So the reason why we move differently than a mouse, keeping everything else aside, only considering a physical factor, we still make different decisions, and that's because of the physical structure. And so a three-dimensional representation of my counter agent, which is going to mimic this mouse, is way better than 2D representation. So that's the goal now. So compared to the previous one, this is the proposed estimation, like post estimation stack. So earlier, if you can see that there's this video feed which will go into model A and it'll give you 2D key points. But now we are proposing another model B, which will take in these 2D key points and it will output 3D key points, which we'll use for option behavior and all that. So earlier we were focusing on improving model A, but for this semester we were working on building a new model, model B, which will take in 2D points and it will output the 3D points. Okay, so before we go to the next one, so to do this, we basically need some sort of a function approximator, right? So one thing is we can kind of look at the mouse geometry and we can predict the 3D key points from 2D key points by applying joint constraints and all that. But it wasn't as straightforward because there were too many flexible joints, and even we don't really have the exact mathematical model of a mouse. So to counter that, what we're doing is we're simulating the whole thing and we're trying to build a data-driven model instead of a mathematical model. So this data-driven model will look at the 2D key points and it will predict the 3D points. So to do this, what we've done is very similar to the previous semester work. So first we've taken a mouse and we've built an arena that replicates the arena that our first model was trained in. So model A will look at images and it will output 2D coordinates. So this setting, we are trying to replicate it on Blender, because Blender is able to render and give us real lifelike coordinates and all that. And also the other good thing is this mouse model that was given to us kind of has all these joint coordinates, sorry, joint restrictions and all that implicitly in it. So with this, I was able to generate a data set, like 2D to 3D data set very easily. And here are just some specifics about the workspace that was replicated. Okay, so let's go to how we're generating 2D and 3D data points. Yeah, first step is pretty obvious. Spawn mouse at random. So we're just spawning the mouse at random positions and different orientations across the workspace. And the next thing is, if you look at this image, there are 12 key points. So we need to identify these 12 key points in the Blender model. So it's as marked here. So you can see that it runs from 0 to 11. So these points are the ones that we wish to have the 3D coordinates and 2D coordinates for. Let's call these points desired points. I am naming them P's for a specific reason, because later this is something that comes up. We will look into it. Okay, so this is it. Right now, what happens is these P points on the mouse aren't exactly free variables, right? So because of the constraints that are there, obviously I won't be able to move all 12 points freely. I'll only be able to move a certain points, and then the other points get fixed because of the constraints. So these points that I can freely move are essentially called Blender control elements. We'll call it that way because the points that we are desired to get the 3D points, and the parts of the mouse that we can freely move are quite different in the model that was given to us. So because of that, the points that we can freely move, let's call it C's, like C1, C2 until C10. And the 3D points are going to be P1, P2. So that necessarily means that as I move these C1, C2 randomly, I'm going to get a certain pose. So that's basically P1, P2, the decide points. Now if you look at the mouse, okay, so there's an image here which is an example. So we moved one of those control elements and we have obtained a different pose for the mouse. Okay, so as we go to the next part, I'll talk about this hierarchical mouse representation because it helps us generating more data. So let's do this. For each of the points, I'm going to define these bone vectors, which basically map from one point to another point. I'll tell you how it becomes useful later, but yeah, for now this is it, and we essentially convert it to polar coordinates. To give a small teaser, what we can do is let's just look at B10 now. If I have it in r theta phi coordinate, r theta phi form, and if I slightly move phi, I'll be getting a different pose, right? But I know that it's a valid pose because my tail isn't like stretching or something. I'm fixing the length and I'm only changing the orientation. So ideally, this is what we're doing. This is what we're going to do later. So for each 3D pose, P, we'll call the capital pose, capital P as pose. We'll be able to generate bones, and again from bones we'll be able to generate the poses as well. Now let's look at some ways to improve to generate more 2D 3D pairs. This is specifically done for one more reason. So if we look at this Blender control elements, ideally for generating this function that will look at 3D and look at 2D and guess 3D, we need to generate a lot of 2D 3D data points. But when we are randomizing it here, we only have control over C's and not control over P's. So if we are generating true random in C's, since it's going through a certain function, it won't necessarily generate a true random in P. Because of that, no matter how many data points we generate in randomized C, we will need to, it will come up with a bias, and we need to come up with techniques to reduce the bias. So that's why we use these data augmentation techniques to generate more training data as well as to reduce data generation bias. Okay, so the first thing is called crossover operator. So what we do here is we have two parents. If you can see to the left, there's one blue and there's one red mice. That's like right next to each other. So what this crossover does is going to select some bones from the first parent and some bones from the second parent. We can see that in the mathematical notation. So that's just random choice of bone A and bone B. Like from parent A some bone and parent B some bone. So like this, I'll be choosing random data points from the data set that I have, and I'll be as parents, and I'll be able to generate new children, and I'll add it back to the new data to my previous data set. So that way I'll be able to generate new data set with lesser bias and more data points. So this is crossover operator, where I take two parents and I produce an offspring. The next thing is called mutation operator. So here what we do is very similar to what we spoke in that slide where we were rotating bones. So what we do is, let's assume we have a pose. We're going to rotate some bones of it to generate a new pose. So simple as that. So that's why we converted all those bones to polar coordinates, so we can do this slight rotation here and there. The one more thing that we need to look at this is the other key points, specifically hand and tail, like hand and legs, aren't necessarily one bone, right? So it has many bones in between. So we can't really say that the distance is going to be fixed. Meanwhile, if you look along the spine, all those parts are like a thread. So we can make an assumption that the distances don't change much. So because of that, whatever mutation that we do here, we only do it over spine. That way, even in data generation, we'll be able to get more mice curved here and there. So that will be more generic. It will reduce bias again. So this is the evolution process of the data set. So initially we get some data set. Let's just say we have some 100 points, and we're doing this evolution process over some 10 generations. So what we do is, first, from the 100 data points that we have, we choose two parents and we get an offspring and we mutate it and we add this child into our old data set. So this way, if we keep continuing it, from an initial data set of 100, we'll probably go to some 150, where this new 50 will help reduce the bias of the previous 100, as well as give us more training data points, which are valid data points, not just random, and meaningful points, because we're not just reusing the old ones, to train our neural network better. Sorry, train our function approximator better. So to do that, we have followed this certain neural network architecture. This is specifically because there's not many 2D, 3D lifters that has been done on mice, but I've seen many 2D, 3D lifters on human data set, on human data sets, yeah. And for that, they majorly use all these cascaded type neural networks, or they either use graph neural networks. So here, for this specific experiment, we're going ahead with the cascaded neural network, because we're using graph neural networks for the policy network later. So for now, we are experimenting with cascaded deep neural networks. To do that, okay, so we see here that the input block has 2 cross 12. So that's basically 12 key points and 2 dimensions. And the output is 1 cross 12, because we're just producing the third coordinate, like the height for each coordinate, height for each key point. So once we get that, we can just put them together and get 3 cross 12, which is the 3D map of the mouse. And these are just residual blocks in between. So we have a decent amount of dropouts. We have enough. We have 5 blocks here, and then it's big enough to learn any representation. A similar neural network did well in the human data set, and so this is going to be easier to predict. So I've used the same thing again. So these are some results in data augmentation. So the first one experiment was 0 generation. So 10,000 data points I generated on Blender, and I just used them directly. And for experiment 2, I used 5 generations, and for each generation I kept getting new offspring. So first one had like 1,000 new offsprings, next one 1,099, 1,209. So I got more data points, and then I put them all together, which was 16,000, and I split it as 75, 25, and I trained it. Again, on experiment 3, I had it kept going up. You can see the numbers on the slide. The last generation produced 2,300 new data points, and in total it went up to 25,000 data points. Again, I split it to 75, 25, and it trained. And clearly, from the graphs, you could see that it helped with the accuracy and loss because of going down, because of the bias going down, but we could probably look out for other metrics that could help us. So visualizing the whole thing, we can see that the top rows are cases where it predicted decently. So blue was the actual one and red was prediction. So looks like for the more probable mouse poses, it did predict well, but for the weird ones, it predicted bad. So it just means that it can be deployed in real life. So it's doing a good job, but it also means that when we're randomizing and generating data set, the above ones are more likely to occur than the below ones. So this is something we need to keep in mind. When we go for future work, I'll start with 2D, 3D post shifting, because it's just continuation of what I discussed now. Now, one important thing is the quality of data generation. Since here we try to randomize C's, and then we try to reduce bias by doing all this, instead, if there is some way we can directly generate data that randomizes P's, by that I mean we're able to generate more natural data, then that'll be really good. And we can also use graph neural networks, because they kind of make sense that the closer nodes affect the current nodes better than the last nodes. So something like that can be used. And for 2D post estimation, so that is basically we can complete the GAN idea by working on a better inverse function that goes from P to C, and this was discussed in the last term of my project. And for behavior discovery, lately, like this year and last year, there's been new papers that has come out, and so they can be used, and we can probably observe better behaviors. And there's also graph neural networks, because these agents are physical agents, right? And physical agents, all the physical structure can be discussed as graphs, can be represented as graphs. So graph neural networks or policy networks will also improve the behavior discovery part. I thank you for the opportunity given to me.